Alright, the purpose of this video is superposition, describing superposition and how to calculate for superposition. I am doing a homework example. We're going to get to that at the end. It'll be the last thing we do. We, in class, had discussed this, and everybody had kind of forgotten how to do regular first year DC theory stuff. So we're going to start there. If you remember how to calculate for series resistors and parallel resistors, you can skip down to the video where you see this drawing here at the bottom right hand corner, or even further if you want to get to this one. This is just going to describe kind of how superposition begins. So I'm going to start with the elementary first year DC theory level 2 of how to solve for resistors in series and how voltage and current interact. I'm going to move into parallel and then into superposition. So this video is going to be a little bit longer than the ones I'm trying to create. So in series, if everybody remembers correctly, we had peer. So hopefully everybody remembers the peer system. And we had P in series, P total equals P1 plus P2 plus P3 and so on. E total equals E1 plus E2 plus E3 and so on. I total equals, so current was the same throughout a series circuit. That's hopefully something we remembered with little to no effort from first year. I'm going to make my pen a little bit bigger. And R total equals R1 plus R2 plus R3. So if we remember correctly, series wasn't too terribly bad to solve for all this stuff. So when we do this, I'm gonna make a pure chart for everything. And we probably won't solve for power in any of these today because we really don't need to. If we remember correctly, with pure, P equals I times E, so we're not gonna get too wrapped up into that. So with a 10 ohm resistor and a 16 ohm resistor, an 8 ohm resistor, and an 11 ohm resistor, we see that R total equals R1 plus R2 plus R3 plus R4 in this case. So we'll bring up our trusty calculator and we will put in our values of 10 plus 16 plus 8 plus 11, and that's going to give us a value of 45 ohms. So I'll bring that up here to my totals. With a source voltage of 12. So if we remember in peer, we take our E of 12 and we divide it by our R of 45. So I will take 12 and divide it by 45, and that is going to give me a value that's a little small for you. We're going to call that 0.267 amps. This one's pretty simple. 10 times, so E equals I times R, or we multiply up with peer. So that's 2.67 volts. We'll go to our next one where we have 16 ohms. So 16 times 0.267 gives us a value of 4.27. If you can see patterns, you will see that the 8 ohms is half of 16, so this will be half, but we'll do the math anyway. 8 times 2.67, 8 times 0.267, 2.136, 2.14. And then 11 times 0.267, it's going to give me a value of 2.94. All right, so that's how we solve for all that stuff in series. Now we're going to move over here into parallel. If you remember in parallel, voltage in this power is still additive. P total equals P1 plus P2 plus P3. And in this case, where in series current was the same and parallel voltage is the same. Hopefully we remember that. Current is the one that is additive. And then this is where it got a little trickier, because R total, we had 3 different ways we could solve for R total. 2 of them were conditional, right? One of them was if they were all the same resistor value, I could put the value of one resistor divided by the number of resistors. Or if I only have 2 resistors, I had what was called the product sum method, R1 times R2 over the quantity of R1 plus R2. But the one we all fell in love with in first year was the reciprocal method, 1 over R1 plus 1 over R2 plus 1 over R3. What we would use for that was the x to the minus 1 button, which is over the number 7 on your calculators. So when we do this equation, we're going to take, and we'll do our pure charts again, EIR equals 100, EIR equals 150, and EIR equals 200. So when we take our calculators and we solve for this, now my calculator on the computer is a little bit different than the calculators that we have here at the JTC. So I'm going to have to take my 100 and do the 1 over x plus, and then you're going to hit x to the minus 1 on that, 150, and you guys are going to hit x to the minus 1 plus 200, you guys are going to hit x to the minus 1. Then we're going to hit equal, and that's going to give us our denominator value, and then we're going to hit x to the minus 1 equals again, and we're going to get an R total, in this case, of 46.15 ohms. Again, if we remember correctly from first year, our R total in a parallel circuit has to be smaller than the smallest resistor, so it is smaller than 100 ohms. Hopefully that is going to be our quick reminder of how to do series and parallel. Oh, in this case, if we have a voltage source, we'll just make our voltage source 600 volts. And 600 volts, again, voltage is the same in parallel, so these are all 600 volts. So if I take my 600 volts and divide it by 200 ohms, I will get 3 amps. My 600 volts divided by 100 ohms gives me 6 amps. And my 600 volts divided by 150 ohms is going to give me 4 amps. Now I can just add those amperages together, right? We saw that I total equals I1 plus I2 plus I3. So I should get a total of 13 amps here. I can verify that by taking my 600 and dividing it by 46.15. And you can see that since that 46.15 is a rounded number, it won't be exactly 13. So 600 divided by 46.15 is going to be a value of 13.00108. So I think we're in pretty good shape. All right, so that is how to do series and parallel circuits. Now we're going to move in here into superposition. And superposition, this isn't really well, it technically is a superposition type of circuit, but this is not where we're really going to get into the superposition where we have different current paths. This has only got one current path. If we remember in DC theory level 2 series circuits, we have our current flows from negative to positive using the electron theory of current flow. So this is going to be negative to positive from voltage source 1. And with superposition, basically what we're going to do is we're going to act like one of those voltage sources isn't there and solve for the circuit. And then we're going to remove the original voltage source and act like it isn't there and replace it with the one that we acted like wasn't there the first time. That sounds confusing. I'll clear it up. So in this case here, we're going to start with voltage source 1, or E1 in this case. And we know that the current flow, because of voltage source 1, is going to flow this way. And we are going to act like voltage source 2 does not exist. We're going to basically jumper that out. So we're going to create this here like that doesn't even exist. So when we go to solve for that, we have got voltage source 1, which has 30 volts and a resistance value of 12 ohms, and that is going to give us 2.5 amps. But let me bring it up on the calculator. 30 divided by 12 is going to give us a value of 2.5 amps. All right, now we're going to take and we're going to put voltage source 2 back in the equation. And we're going to act like voltage source 1 doesn't exist. And my current flow through voltage source, because of voltage source 2, negative to positive, is going to now go this way. So now we solve for this one. We've got a voltage source of voltage source 2 of 24 volts and a resistance value of 12 ohms. And that's going to be 24 divided by 12, which should give me 2 amps. And we do. So, perfect. Now what we have to do is we have to look at each resistor. In this case, I've only got one resistor, so I can see that up here, and that is where I see that I've got those two current flows, because of voltage source 1 and voltage source 2, are flowing in opposite directions. So since they are flowing in opposite directions, they oppose each other. So my totals over here are going to be this 30 volts because of voltage source 1 minus 24 volts from voltage source 2. If those currents were flowing in the same direction, they would be additive, but they're not. The current flows are in different directions. So I'm going to subtract 30 minus 24, and that's going to give me a value of 6 volt source, and I'm going to have my current flow 2.5. This is E. My current flow is going to be 2.5 minus 2, which is going to give me a total current flow of half of an amp. And again, my R total, we already know, is going to be 12 ohms. So we can also see that my pure chart works for that as well. We didn't really need to do superposition in that respect because, if you remember correctly, those are series opposing voltage sources, and I could have just taken my 30 minus 24, got the 6 volts. But that doesn't do my example any favors, does it? All right, so now we are going to move on. Oh. I don't want to just move that. Sorry, technology. All right, now we're going to move over. This is actually a sample off of your homework. And I will try not to muddy it up too much. If you want to look on it at the same time, this is lesson 1, DC Theory 5, lesson 1, question 14. So, again, now in this case, we do have two voltage sources that are the same. They are both 24 volts. If you have two voltage sources that are the same, we're going to use voltage source E1 as our primary, and voltage source E2 will be our secondary voltage source. So our reference is going to be voltage source 1. If you have voltage sources that are of different values, then your higher voltage source is going to apply the most pressure. That's the one you're going to use as your primary. So everything's going to be in reference to voltage source 1 in this case. So what we have to do with this example is we have to jump out this battery. Voltage source 2, we're going to jump it out and act like it doesn't exist. And now that we've jumped it out and acted like it didn't exist, we're going to use voltage source 1, which I'm going to use red pen for. And we have got to figure out what our current flow is. Negative to positive, so our current flow is going to go this way. Here it's going to branch off like so. Current flow is going to go this way, and its current flow is going to go that way through that resistor, that way through that resistor, and that way through that resistor, and back to source. So we have to redraw this just like we did in combination circuits. So it is going to go through, when we redraw this, those numbers are pretty blurry. So it goes through resistor R3 and R2. This one's R3. And this one's R2. And this one's R1. So it goes through R3 and R2 first. So here's R2. And here is R3. R2 has a value of 100. R3 has a value of 250. Then those current flows come back together at this point and they go through R1, which is 100 ohms. All right, now we have to use our parallel rules and combine R2 and R3. When we combine R2 and R3 and R1, so R2 and R3 combine together. I can use reciprocal method, the 1 over X, or I could use product sum. In this case, I'm going to go ahead and use product sum. It's 250 ohms, which is R3, so 250 times 100, R2, divided by the sum of those two, which is 250 plus 100 is 350, and I'm going to get a total resistance of my parallel branch of 71.43 ohms. And now that I've got the 71.43 ohms and the 100 ohms in series, I can solve for my R total, which is 171.43 ohms. I remember that my source voltages were both 24 volts. If not, you can go back up to the picture and look at it. You'll be fine. So now I got to solve for I total. So I'll bring my trusty calculator back up, and I'm going to take my 24 and I'm going to divide that by my 171.43. If you leave that in your calculator and you just hit second answer, you'll get a lot more accurate response. But in this case here, my calculator says I have got 0.14 amps. When I go from, and that's everything I need to know about the totals, now I got to go back up the circuit just like we did in DC theory combination circuits. So I think that's level 4. In series, we said current was the same, so I'm going to bring my series or my current back up here, which is 0.14. I'm going to multiply this 100 is the easy one. I just move the decimal point over 2 places left. That gives me 14 volts. Hopefully I remember Kirchhoff's law, E total equals E1 plus E2, and that's going to mean that this is going to be 10 volts. If we don't remember that, we can peer it, right? We can take our 71.43 and multiply that by 0.14, and I got 10 volts. So now that we have gotten that accomplished for everything in our series circuit, and R1 is completely done, I got 14 volts and 0.14 amps, I'm going to go R2 and R3, and we see that R2, R3 are in parallel, and in parallel, voltage is the same. So I've got my 10 volts and my 10 volts. 10 divided by 100 is 0.1. And I know my currents are additive, so that should be 0.04, but again, I can do the math and do my 10 divided by 250. And I will take my 10 divided by 250, and that is going to give me a value of 0.04. So now I know all the values that I need to know and bring them up here into my chart. And in this case, R1, which is up here. And we know that my current flows that way, so I'll put my E, I, and R. resistor 1 is 14 volts, 0.14 amps, and 100 ohms. R2 is 10 volts, 0.1 amps, and 100 ohms. And really the ohms are important because we're solving for voltage and current. And R3 has 10 volts, 0.04 amps, 250 ohms. That solves everything for voltage source 1. Now we got to come through and we've got to solve for voltage source 2. And in order to do that, now we're going to jump out voltage source 1. And I like to figure out which way current is flowing first. We can do that last if you want to, but I like to figure it out first. Negative to positive means that this current flow is going to go this way. And it's going to branch here. This is going up, so this is going to go the same way. But everything else, it looks like it's going to go opposite. So when we go to do our redraw with this one, it branches off at this point again, and it goes through R1 and R3 first. So now my drawing is going to look like this, R1 and R3. Where I've got R1 of 100 and R3 of 250. And then I go through R2, which is 100 ohms. Now, if we look at what we did in our first redraw, and we look at what we're doing here in our second redraw, those values are all the same, just the resistors are different, right? Where this is resistor 2 here, it's resistor 1 here. But other than that, the values are exactly the same, and my voltage source is the same. So I really don't have to do any work at all. I can just move these numbers that are in R2 over to R1 and say that this is 10 volts and 0.1 amps. And this is 10 volts and 0.04 amps. And this is 14 volts and 0.14 amps. If you want to. If not, you can solve all the way down. That is kind of the beauty of superposition, is a lot of times these values are the same resistor-wise. So you don't really have to go through and do the resistor calculations more than once, but you might have to go through with a different voltage source values. You'll have to go through and do the rest of the math. But in this case here, we didn't have to do that, so yay us. So now I'm going to move my numbers up here to R1, where I've got 10 volts and 0.1 amps, and these two current flows are in opposite directions, so that means I have to subtract them. So minus 10 and minus 0.1. R2, you see those arrows go in different directions, so those are subtractive. So I got to subtract 14 and 0.14. And with R3, those two arrows are going the same direction, so I'm going to add them. And this is 10 and 0.04 again, so plus 10 and plus 0.04. So I'll do my answers in green. When I do 14 minus 10, I get 4 volts. When I do 0.14 minus 0.1, I get 0.04. That's for voltage and current through R1. When I come over here to R2, 10 minus 14 is negative 4. And 0.1 minus 0.14 is negative 0.04. And when I come over here to R3, 10 plus 10 is 20. And 0.04 plus 0.04 is 0.08. That is my, I'll call it quick and easy version of how superposition works.